And now it's time for a key question of numerical analysis. I'm supposed to figure out some integral I. So I choose some method, I choose partition size, and I produce a number, in, which hopefully approximates well the integral. But how do I know if I don't know the precise value of the integral? What is the error? That's the key question. And we had a video on Richardson extrapolation, which works with step size. But this is not a problem because partition size and step size, they are related. But it's actually worthwhile to transform the results of the Richardson extrapolation into the language of partition sizes because it's very useful for integration. Now, I could do it right away without any trouble, but I think it's good to recall the basic idea and show it in the language of partition sizes. So, here is a piece of real line, and here is I, the number that I'm trying to achieve. Now, I will do two experiments, one with partition size n, and the other with partition size 2n, so I can expect it will be better. So the partition size 2n will get me closer, while the partition size n is still not so precise. That's a typical situation. And I'm interested in this error. Okay. I look at it and I say, wait a second, there's also another error here. And if the in is a method of order p, then I can expect that this error is actually 2 to p times e. We talked about it earlier, how the order of a method transforms into the changes in the error. So when I go from here to here, the partition size is divided by 2, and therefore the error is multiplied by 2 to p. And then I look at this distance and I say, okay, I2n minus in is 2 to pe minus e, and a little rearrangement, I factor out e, leads me to the formula that the error can be perhaps I2n minus in divided by 2 to p minus 1. And we also, in this video about Richardson extrapolation, derived a formula for better estimate of the integral, which I'm not really interested in right now. So I think I typed it. I see myself typing it. Okay, here we go. So we have a method of order p, which is specified a little bit better in the formula there. And then there is a formula for better approximation of the integral. And the last row, this is the formula for approximating the error of I to n. And the formula fits. Okay, so first of all, let's have a look whether this really works in applications. So here is an experiment. We have our favorite integral from 0 to pi over 2 sine of x dx, which is actually equal to 1, so we know. I'm applying the formula for left rectangles, which has order 1, and I will calculate the actual error and also the Richardson extrapolation, and I'm using step size 4 and double 8. Here we go. So, when the step size 4 is the test value and step size 8 is the one that I'm interested in, then the one that I'm interested in has error 0.101 essentially, and the Richardson estimate based on I4 and I8 yields 0.107, which is fairly close, so it seems that it works. Okay, let's try to change the method to trapezoids. And therefore, I have to also fix the order. Trapezoid is a method of order 2. And again, there will be 2 attempts. One of them when n is equal to 4 and n is equal to 8. This will be the 2 attempts. This one is the one I want. This one is used for estimating the error. Bang. And again, we compare these 2 numbers, and they are fairly similar. The first 2 valid digits, they agree, which is very nice. And finally, how about Simpson? So the Simpson method has order 4. And again, let's fire it up. And now these are really tiny errors. And again, the Richardson estimate works reasonably well. So this is something nice. Now, to conclude this very short section, let me show you something. I will use trapezoid method, and I'm interested in what happens when n is equal to 8. And I will use Richardson estimate. And I will do it by hand so that you can see what I'm actually doing. So, here I calculate using the trapezoid method with number of steps 8, okay, I think I can skip this one. The integral, roughly. And the value, I8, is about, here we go, 099, let's see, 6785. I can stop here. If I stopped earlier, I would have to round it up to 1, which is the precise value, of course. Now, I don't know what's the error. I actually know the actual value, but I pretend that I am not aware of it. So, if I want to estimate the error, I have to make first a test run with half the step. So I'm going to save this result to a variable called I2 because it's the one that is more precise. I2 is this, bang, it's there. Now I'm going to do another calculation, the one which is preliminary, I1, which is number of steps 4. And here the result is 0.97 and so on. And now I use this formula. Now the order for trapezoid is 2. 2 to 2 is 4, minus 1 is 3. So I will be dividing by 3 and subtracting. Let's have a look at it. So the error estimate is I2 minus I1 divided by 3. Here we go. This is the error estimate. 0.00322 and so on. Now, imagine the following situation. You have a customer, and the customer says, okay, what I really need is an approximation of this integral, and my requirement is that the error is less than 0.00001. How do I do it? Here's the trick. When the partition size is 8, I get error, which I don't know, but it was estimated. Estimated using the Richardson's formula, which we have over here. Now, I argue this way. If I increase the step size, the partition size 8 times, then the error decreases a squared times, because it's a method of order 2. And the requirement is that this should be 0. How many zeros? 1, 2, 3, 4. 4 zeros. 0.00001. This is the requirement for my customer. Well, that's an equation from which I can determine A. How much is A? If I call this one epsilon, which is sort of customary, the required precision, then A is equal to, and I rearrange it, is the estimated error of my first attempt divided by the required precision and square root I take. And I get A, and if I know A, I know the new step size, which is recommended to be used. So let's have a look at it. What is A? A is square root of the estimated error divided by the error which I'm supposed to have in my calculations. So A is about 17, but I need integer, so I round it up. I round it up because I get bigger partition size and more precise answer. So my new attempt will be using n, okay, let me put it just like that, 8 times 18. That's my new recommended partition size. The original partition size was 8. I multiply it by this 18, and I get, let me see, 144. So the new recommended partition size is 144, and just to be on the safe side, I take 150. Okay? This shouldn't make things much longer, and I hope that it will give me what I need. So I go back up here, and I use number of steps 150, and I get some result, which I stored in I2. And this result, you can see it over here. Now, would I know that it's correct? I am not sure, so I will try the Richardson estimate again. So I will have to make another experiment with just half the partition size, which is 75. And I have it over here, the code. So partition size 75. And again, I use the error estimate. And the error estimate is 9 times 10 to negative 6, which is a little bit smaller than this one. The error estimate is 0.123459, which is almost 0.12341. That's exactly the requirement. So Richardson estimate of error tells me that this could be the answer that my customer wants. Just out of curiosity, is it true or not? Let me look at the actual error. So I2 is the result which I want to hand in to my customer. And the absolute value of the difference between I2 and the actual value is, voila, it's almost the same as the, it's really almost the same as the error estimate by Richardson. The last line and 2 up, these are almost the same numbers. So this is actually something which is practical. You see, I wasn't cheating. I never used the fact that I know that this integral is 1. I made an attempt using the Richardson estimate and sort of like half-quality attempt. I estimated my error, and I used the knowledge of the order. This is what I call this indirect proportion, but it's not true anymore because there is this square happening. But this scheme is very helpful. So I use this scheme and the requirement on the error to actually determine how I should modify my step size. And the modified step size actually gave me the answer that I needed. So in applications, it would be too wasteful to simply try increasing n until I get lucky enough to get the right answer, because I could be trying n equal 8, 20, 100, many experiments. In this way, I got it in one step. Very nice. So that's very practical, and it shows that the Richardson estimate not only gives you valid information, but you can also use it to actually predict what's going to happen with your experiments, and you can focus and just zero in on the right answer with very few attempts. Okay? Very nice.